Hello, welcome to my video on simulation and understanding how to do it and how to interpret your simulations. This is a basic video on it, and I'm not going to go too in depth because it gets really complicated really fast, and for a beginner kind of tutorial, I don't want to go too fast. And I don't want to give you too much information all at once. I will make more videos on this, and they will be posted on the 2468 YouTube channel. If you want to look at those, past this, you won't really be needing anything for FRC, because even basic simulation we don't use very often. So I'm just going to jump right in. The first thing you need to know before I start teaching you how to do the simulation is how to interpret what your simulation is telling you. A lot of times when people kind of just start with simulation, they'll do a simulation, they see all these colors, but they don't know what any of it means. Because you get a colorful part and it doesn't tell you, oh, this part's gonna break, this part is permanently deformed, this is plastically deformed, this is elastically deformed. It doesn't tell you what's going on. It does, but it's hard to read. It's kind of hard to understand. So I'm gonna help you understand the concept kind of before I go and I explain what and how to do the simulation. So when simulating, it's really important to understand how to interpret information that Solidworks gives you. And in the case of simulation, that also means knowing what level of stress or strain is appropriate for your part before you've destroyed it or you're going to put too much fatigue on it. So when you do a simulation in Solidworks, you get a really colorful part, and on the right side, there's this rainbow scale, and it's got values all over the side. These colors and values help you determine whether or not the part that you've created is able to withstand the stresses that you're applying to it, and that it's going to be subjected to in the real part world on the bottom. So first things first, I have to show you this graph, because it's really important that you understand what Solidworks is doing and how it's kind of giving you what the data it's giving you means. So you can see that at the beginning here, there is this linear line. At the top, there's a yield strength. So that linear line is where linear simulation is. That is the stuff that regular versions of SolidWorks can do. So first thing I'm going to do here is I'm going to show you a graph. This graph is really important to understanding what the values on the right side of your screen mean, and I could make this a super long segment, but I'm going to kind of keep it short so you can get to the actual simulation part. So the most important point on this graph is the yield strength. Without knowing what that point means, you don't really know what the information the simulation is giving you means. So the yield strength is the point where the deformation on your part becomes plastic. To explain this to you, elastic deformation is the kind of, imagine it like elastic, like you stretch out an elastic band and you let go and it goes right back to where it was. That's elastic. It'll go right back, and it's kind of unaffected when it goes back. There will be fatigue on it, but its geometry and its shape is unaffected. Once it becomes plastic, which is past the yield strength, then your part is essentially ruined. That's where it becomes plastic. If you've ever seen a video of a metal rod having a tension test, a tensile strength test, you can see what plastic deformation is. And necking happens around there. That's where the metal starts to thin out in the middle, and then it finally snaps. And that's what plastic is. If you let go of the rod right when it's starting to pinch and thin out, it's not going to snap back to normal. You've plastically deformed it at that point. It's ruined. You can't use that anymore. So if that's happening to a part on the bot, that is very bad, and you need to avoid that. That's the reason you would use a simulation like this. So also something worth noting, if you don't have Simulation Pro in SolidWorks, anything past this linear line, so anything past the yield strength is not going to yield the correct result, because anything that isn't Simulation Pro can only do linear simulation. So you're going to get kind of fake values that are way higher for the stress that your part can take. So don't trust any of the values above the yield strength. because that's not going to be correct. We are done with the hard part. So now we're going to be moving on to how to actually run these simulations. So I have two examples. Both of them do kind of apply to FRC. The first one is going to be this hex axle. We're going to do a force test to kind of simulate, hey, will this hex axle hold up the force of the bot on it, on a strap? The next one's going to be this bracket. You can kind of guess, maybe you've got a piece of 1x, and this isn't actually a bracket that you might use in FRC, but the example works nonetheless. So we're going to start with this bracket because it's the easiest one to do. So the simulation tab is here, 7 from the left. You're going to click on it, and to start a study, you click New Study. So all of these down here are don't really apply to FRC, or you won't need it. Maybe you'll use Design Study or Topology Study. That's good for optimizing your geometry or your material choice, but you won't really need that. What you will be using more is static, and even then you won't be using it that much. Nonlinear is the kind of thing you'll use when your simulation is getting past the yield strength, and you won't need that in FRC. So we're going to go with static, and we're going to call this bracket test 1. We're going to click check, and that's going to create our study. So you'll get this little UI here. You'll notice I already have my material defined up in my part, and it's always good to define your materials. I'm not great about it, but I'm trying to get better. Always define your materials when you get the chance. It helps with determining the weight of the bot, whether or not a motor can handle turning around your shooter or picking up your intake. Really, really helpful stuff. So if you have that set, most of the time it'll carry over into here. If it doesn't, you won't see this little name in parentheses. The first thing you're going to want to do is set the material, because it's really annoying when you set everything up and then it throws you a bunch of errors and you have to go back and set your material. It's really easy though. Just right click, click Apply and Edit Material, and then pick your material. Right now I'm using the material we use, 1060 alloy, it's aluminum. Click Apply and then close it, and then it's set. So the first thing we're going to do to set up this simulation is we need to set fixtures. So think of fixtures as kind of your mounting points. So let's say we're trying to simulate this bracket being pushed this way, this face being pushed this way by anything. It doesn't matter what it is, but it's being pushed this way. And it's being held down by bolts in all 4 of these holes. The points that aren't moving are those holes. So we need to make those fixtures. It needs to have something tangible to lock down on in the simulation. So to make those fixtures, we're going to right click, go to Fix Geometry, and there are plenty of other kinds. There's bearing fixtures, elastic ones. Right now for the basic simulations, we're just going to go with Fix Geometry. And this is very brute force way to do it, but it works, and it works fine. So we're going to select these holes, and you just have to click on them. You don't even have to hold Shift or Control. You just click on them, and it selects. This GIF here is actually a really good example of what it does. These holes cannot move. No matter how much force you apply on them, they will not move. And that's how you kind of ground the simulation. So once you have these holes selected, you have one part of this done. Next thing you got to do is you have to determine what your external loads are. So these are the things that are going to be kind of pushing on your model. Now we're not doing contact simulation. That would be where I had another model in here and it was pushing against this, so you could simulate how they interact. This is simply testing this part, so it's not going to have any interaction with any other parts. So we're going to right click here and we're going to pick which kind. Now in this case I'm just going to use force, and I'll show you how we're going to use this. So if you want to think of this, let's say we've got a piece of 2x1 here, and this piece of 2x1 is being pushed this way by something. How do you simulate that? So the first thing you got to think about is, how is your piece of 2x1 being mounted to this? It's probably by bolts, so your force is probably in some way, shape, or form coming from these holes. So let's select the holes. Okay, so now you might notice this doesn't look right. All of your force vectors are going out from the holes, and that's certainly not where your force is actually going. It's going this direction, right? So we have to select a direction instead of normal to, because normal to will just create a normal vector to the face that you're selecting. So now that you have selected direction, you're going to want to pick a line that is running in the direction you want it to go. It doesn't have to be pointing. It's not going to tell you which way of the two directions because it's a line. It has two directions. But you just want to find a line that's going in that direction. So you click this and you'll notice all of these lines are now aligned in this. They're parallel to this. So, but they're kind of going the wrong direction. We want to simulate a force going this way. So what we're going to do is down here in force, we're going to click reverse direction. This makes our force go outwards. And we're going to do this in freedom units. Let's go to English. So let's say 25 pound-feet of force. Now, we could do non-uniform distribution. I'm not going to do that right now because that's more of an advanced feature. These are the basic components. You need fixtures and then forces. So we're going to click check. This is all set up. We've got these going in the correct direction. They're pushing on the correct thing. If we clicked on this face, it would just be uniform and it would push all at once, which isn't really realistic of bolts. So we're just going to keep it with these. We've got our fixtures for our other bolts here that aren't going to be moving and that we trust not to move. So we're going to click check, and because we're okay with that. So we could try and run our simulation now. Now if we click just run this study, it will run, as you can see. I'm going to cancel it though. Okay, so instead of just running the simulation, what I'm going to do is I am going to create a mesh for this. So I'm going to right click down by mesh, and I will click create mesh. Now we are going to, I'm going to explain this to you as best as I can. So you can see in this picture how this has kind of got like the part file look, but it's got all these triangles in it and these boxes and lines. So I'm going to quick mesh it. I'm going to go to kind of around there, and then I'm going to click check. So what these are, they're like voxels. They're 3D pixels. So when forces are applied, they will deform and they won't change volume. They'll keep all of the properties that they previously had, and they won't change, but they will deform in shape. Just not volume. So you can see it bend over, you can see all sorts of things happening to your model, and you can see how it's deforming, but it will not increase in volume. If something does increase in volume, something is wrong, and I will show you how to fix that later when we come across that problem. I will intentionally create it to show you what it looks like. So this is meshing. This is how Solidworks kind of looks at the piece and says, or it has a starting point, so it knows what to do when you run the simulation. So now that we have mesh the piece, it's ready to be run. So we're going to come up here and click run this study. Okay, so now we have this wonderful looking colorful piece. So the first thing that you might notice is there's these gradients all over the place, and you kind of might want to know what these colors mean. So if you look over here, this is the force that's kind of, and stress that's been applied in these specific areas, and they correspond with colors. So this red here corresponds with this red, which is 4.194 times 10 to the 8th Newton meters of force. So that's a good way to kind of, this is how you gauge where your piece is weakest and where it needs to be built up, reinforced, and how you need it and how you can make it better. So if you remember from the last kind of intro part, we talked about yield strength, and this is where your yield strength is, this little red line. So anything that's above this color has passed your yield strength. So this part is not good for this amount of force on these 4 pieces. And I might add that this is per item. So each one of these arrows is a whole 25 pound-feet of force. So this is a lot of force. That's what, 8, 1, 2, 3, 4, 5, 6. That's like 20. That's 24 times 25. I'm not even gonna do that. That's a lot of force. So this is kind of that's an unrealistic amount of force to be putting on this. So you might be wondering how you would figure out which parts are actually under all that load. Like, you can't really tell what blue is what. Like, where in here does it stop being under the yield strength and start being above the yield strength, so I know where I need to improve this part, or where I need to, say, add a rib, or what needs to be improved. So there's a good way to do that, and it's really great. SolidWorks does a really good job of this part that not a lot of CAD softwares do. So if you right click here, you can right click here, or you can right click here. You right click, you go to ISO clipping, and this determines which one of these values indicated by this black line it will filter out. So if you ever use a camera, your ISO is the light sensitivity. ISO in this case is stress sensitivity. So as you lower this value, more and more volume starts to appear. So that black line is how much it's allowing. Everything above this is allowed, above that black line. So if I lower it and I go, let's try and go just above. Okay. All of this is above the yield strength. So all of this is permanently deformed from all that force. So that tells me that I need a rib that's maybe starting around back here, coming all the way up to here. That'll help me reinforce this piece, and it'll help it kind of have more tension. So this is really helpful for making informed design decisions. Now, sometimes what'll happen is if it doesn't deform quite enough to be obvious, like if you click here, get normal to this, this is an obvious deformation. Like this is very clear that our piece is bent. Sometimes it'll do things where if you come into settings here, definition, it will do something like this. Like that. Okay. Sometimes it'll do something like this to make it unbelievably obvious. And this is obviously very exaggerated, but you've noticed when I mentioned that the volume shouldn't increase, the volume increased by a substantial amount. This piece is significantly thicker here than it was when it was normally set up, like here. And if it gets high enough, and I'll show you what that looks like because it happened to me earlier, let's say it was like 15,000, something outrageous, it will just completely break SolidWorks, and it doesn't make any sense. Like, what is even going on here? Those are our 4 fixed points, and look, despite the value being so high, they still haven't moved. But the rest of the parts kind of increased exponentially in volume and size and everything. So the good way to check that is if the deformation scale is above 1, probably set it back to 1. SolidWorks likes to do it just so you can kind of see where your part is moving and bending, but go to true scale or just user define it as 1, and that'll work either way. So the automatic in this case was 2, or roughly 2. So now you can see accurately what this looks like. Let's say you want to visualize your kind of three-dimensionally what's happening to your part. So I'm going to click here on the stress, and I'm going to do section clipping. Section clipping is what you're probably more familiar with as a cross-section. So you can kind of see inside the part what is wrong, what is being the determining factor in your issues. So this is really good for things like hex axles. If you see that, I think it's Thunder Hex has a complete hole through it. If you see that there's an issue because maybe there's a hole in the middle and there's a lot of strain in the middle, you might not want to use Thunder Hex. So this is really good for determining which parts of your part are the actual issue, because clearly here it's not the inside, it's outside loads. So you don't really need just a stronger material, you need better bracing on the outside. Okay, now we're going to move on to this next part. This is a hex axle. So there's a lot of ways we could test this. We could do a torque test, but I'm just going to do a load test, just straight on the side. Say you've got this hooked up to your bot, you've got a bearing here, and this is going to lift your bot straight up into the air. Now obviously you'd need a specific number for the load, and I'm just going to make one up just so we can teach you an idea of how this is supposed to work. So in this case, we're going to do static, do hex axle test 1. Okay. Now, just like before, we're going to need fixtures. But things like this are a little more complicated. Because normally if you design this hex axle, oh, didn't mean to do that. Normally when you design this hex axle, it'll look like this. You will have just a solid face. Where are you going to put your fixtures? It's not really realistic to put them out here because that just doesn't make sense. It's not fixed at the face. It's fixed somewhere along this length. So it's really important to use split line. Split line allows you to have a split here. So you can literally select a face that is sectioned off. And I'll show you how to use this real quick. So split line. We'll create a new split line. Okay, so we're going to make a new split line. We're going to do a projection, and I need to make a new sketch actually. So we're going to do it from the front. No, we're going to do it top plane. Top plane sketch. Yeah. And then we're going to make a line down here. We're going to make it some arbitrary length from this, like, I don't know, 3 inches, because that was close. Okay. Now, and actually we could use this. This could be pretty helpful. Oopsies, didn't mean to do that. Vertical. Okay. So we've got these 2 lines. Make sure they're not construction lines. That's very important, because construction lines will not work. So we're going to go back over to our feature tree. We're going to go split line here. Split line. Now you're going to want to select the sketches that you just made. So in this case it's sketch 5 for me. And then I'm going to go to projection. It starts on silhouette, I believe, but I'm going to go to projection because it's the only one you can use a sketch for. And you're going to want to select all of the faces that you want this line to be projected onto. Okay, so now I've got all of the faces. You click. Okay, so I ran out of space on my recording. I just finished the split line example. So that should be good. I'm going to just start with the simulation thing again. So new study, static. Test 1. Okay. Now you guys already know fixtures are going to go around here because this is where the bearings are going to be. So we're going to go here, and I'm going to select every single face that the bearing might be in contact with. Here, 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 here. Okay. Boom. So you've got that. Now we need to get our forces set up. So because we did the split lines here, I am going to just apply a force in this middle area because this would be where our spool is, and that's the only spot where the force is being applied. So we're going to add an external load. It's going to be a force. We're going to click here. Now the direction's already normal. We don't need to do any weird selected direction stuff. It's already going the correct direction. So after that, we're going to click actually freedom units and set the force to, let's do 25 pound-feet because that's what we did last time. I'm going to click check. And that, by the way, that 25 pound-feet is arbitrary. I'm just picking that out of thin air. You will actually need to find the force of your bot in order to properly calculate that. So now that we have almost everything set up, we're going to mesh it. I'm going to go to create mesh. I'm going to make this a more fine mesh. And this just means it's literally mesh density. It means it's got more little voxels in it. I'll click check, and you'll see what I mean. Compared to the other mesh, this one is a lot more detailed. There's a lot more triangles in it. So now we are going to run the study. Okay, this is a perfect example of over-deformed, way too high scale. Look up here. The scale is 1342.48. This is not what your thing is going to look like in real life. Alright, that's absurd. This is an alloy steel axle. To do that to an alloy steel axle would take an absurd amount of force. So, let's go to displacement. Let's right click. Let's go settings. Definition. True scale. Check. That looks a lot more normal, I think. Stress 2. Settings. Definition. True scale. Check. And strain. We're not going to use strain as much. Strain, I'll have to explain the difference between strain and stress in a second. Okay. So, first we're going to go to stress. So, first thing you might see, because this is the next step, you look at your yield strength. Where is my yield strength? It's not, there's no red line here. But notice this goes plus 0.01, 0.06, 0.07, but my yield strength is way up here. It's way higher. Basically what this is saying is I'm not coming anywhere close to my yield strength. And this is good. So this probably isn't the weight of the bot, but this is telling me that this side load is perfectly reasonable for this hex axle to handle. Now, if, say, we still wanted to do iso clipping, you want to see where the most force is at, and it'll tell you lots of force at the areas outside the bearings. There's lots of force immediately in front of this load and on the other side of the load. Whether or not you need that, it's yours to decide. Displacement, this just tells you which parts are moving furthest away from their original position. This thing is moving. Look at that number. Red is 2.6 times 10 to the negative second millimeters. That is tiny. There's basically no movement. Strain, real quick, I want to touch on this. Strain is, think of it like this. If these triangles, these are the mesh triangles. If these triangles are 3D pixels, then stress is strain but with anti-aliasing on. It is smoothed out and made to look more realistic. It helps you analyze better how the force is distributed throughout, because it's a little hard to read that from this. It's a little bit hard on the eyes and it's hard to understand. So, stress and strain are basically the same thing for all intensive purposes, especially in FRC. You don't need to know any difference between them. So, then from here, again, in case you want to see, say, I'm going to teach you probing. Probing is really useful if you want to know the value in a specific place. So say you're a little worried about this spot right here. You can click and you can see exactly where this is. And I happen to get really close to this top. It's like right around here. And it'll give you all of this information about that node. So, let's quick cancel that. So the probing is really, really nice. So you just click a spot, and now you have information about that spot. So now you see the force on it, 1.875 times 10 to the 7th Newton meter squared. And now you know the force in that 111 specific point. It's very, very fine space. You can click anywhere in the part. In fact, I'm pretty sure you can just go here. So let's say you wanted to see what it's like on the inside. A little closer to the middle. You see all these spikes and you're a little worried maybe. These spikes are actually kind of artifacts of the voxels that are used to generate this mesh. But we can leave that there, and then we can go here and we can go probe, and you can probe inside of the part and see values inside. So in here, there's like barely any force. That's what, +6. That's somewhere down here. So really great for figuring out where you're having most of your forces distributed. Okay, also while I'm here, I am going to teach you how to do non-uniform distribution. This is a little bit more advanced, but I think it's kind of helpful because there is rarely a case where your forces are distributed as nicely as this, and it doesn't make sense to rely on that kind of a thing. So, real quick, I'm gonna start from the beginning. I'm going to delete this study, and we're gonna start fresh. So, new study. Make sure it's static. Oh. Okay. Check the material again. We're gonna go to fixtures, the fixed geometry, of course. And then click check. Now we're gonna go to external loads. And this time we are going to be adding a force. So, this is where it gets a little more complicated. We're going to click on the side that we want the force. We'll say, again, 25 pound-feet of force per item. Now we're going to go to non-uniform distribution. Now, this is, here, actually, we can uncheck this for now. I'm just going to set that up. Non-uniform is exactly how it sounds. All these arrows are set up in places so that they're like perfectly symmetrical. Like if you drew a line right through these two arrows, this side matches up perfectly. Draw a line across here, this side matches up perfectly with that side, and it's super symmetrical. But in order to get non-uniform, we need to have a reference to something other than just normal to the face. So we need to create a coordinate system. So we're going to come over here to features, and we're going to go to reference geometry, create a coordinate system. Now, first thing I am going to do is I'm just going to map this to these, and it doesn't at the moment. We'll say this is the right plane, we'll say this is the top plane, we'll say this is the front plane, and then we'll say, we'll say that this is the origin. So you're literally setting your axes here. So right plane is, I didn't mean to do that, right plane is the x-axis, the y-axis is the top plane, z-axis is front plane, and the origin is this origin. So now click check, and now we have a coordinate system set up in this. So now we're going to go back into our force, edit definition, and we're going to select non-uniform distribution. We're going to go here where it says select coordinate system, and we're going to click our coordinate system, and these are various ways to do it. This is the way probably everyone is familiar with. This is where it gets messy, and I don't even know what's going on, and I'm not going to get into it because I couldn't tell you what to do. And we're going to go inches, and this is going to generate a random distribution for us. Now we're just going to come here, and it's going to non-uniformly distribute our forces. So now you can kind of see what's going on. These arrows, these vectors, these force vectors are really small. These ones are bigger though. You can see the size difference. Now you can see that these forces are non-uniformly distributed. Really, really good way to kind of determine how your thing might respond to, say, maybe the strap starts spooling on this side, but there's still going to be some force over here. Without doing contact, a simulation, which is a lot more complicated and takes a lot longer to simulate, this is a good way to get like a rough idea of what's going on. So I'm going to quick mesh this, make it a more fine mesh. And then, by the way, if you need to quickly just do this, you can just click mesh and run, or you can just click run. Go back over to simulation, click run the study. Okay. Now, what is, or should be, sort of immediately obvious, it's the same as last time almost, but it's pushed a little over to the side. Not much of a difference. It's still a very similar result. You're probably going to have higher forces on this side here than you are going to have over on this side. as seen visually. That's basically it. Those are the basics of simulation in SolidWorks. There's a lot more to simulation. Like I said, I skipped over earlier, probably what? Nonlinear simulation. There's contact simulation, contact modeling. That stuff's really good if you say actually want to put bearings on this and you want to see maybe how the bearings will behave inside your piece of 2x1, or you want to see how your wheel will behave when it's subjected to a lot of load and this hex axle is through it. If you want to see how things interact, there's contact modeling. I will consider making more videos about those because there's a lot more than just this in the simulation area of SolidWorks. If you're looking to do things outside of just basic stress modeling, because SolidWorks cannot simulate the actual destruction. Say if I put this under 1,000,000 pounds of load, pound-feet of load, it would break, but SolidWorks can't simulate that. So that goes into SimilarWorks and other software that's developed by Assault Systems. I can't do that because I don't have a license for that, but I will make more videos for simulation in slightly more advanced methods.